Right. So electromagnetic waves, and the first topic would be Maxwell's. Okay. So what are the Maxwell equations? And yeah, so before we start this Maxwell equation, let us understand that what did we understand in the previous chapters, right? So in the previous chapters, in chapter 4, what did we see, Aisha? In chapter 4, we saw that we had, yeah, so in chapter, we saw that there was some current moving, and these were producing some magnetic field. So this is electric current producing some magnetic field, right? So charges were moving and they were producing some magnetic field. This we understood, right? And in the fifth or sixth chapter, we saw that, right? In chapter 6, we saw that change in magnetic field, produces the electric field, right? Electric field or electric current. So this we saw, right? And we saw that magnetic field is generated whenever we have these currents, right? So is this possible that we have, is this possible? So the question is that, is this possible that change in electric field produces magnetic, right? Because we are seeing that the magnetic field are produced by flowing charges, right? Due to the flow of current, the magnetic field is produced. But in the case of magnetic field, we saw that whenever we change magnetic field, this produces the electric field. So let's say that if we change this electric field, then can it possibly produce this magnetic field? So this was the question. And Maxwell did some different experiments, and he found out that yes, so he found out that yes, it is possible, right? So up to this point, we saw that only change in magnetic field can produce this electric field. But what about the change in electric, right? Okay, so moving on, right? This was the idea. And then there was this experiment, right? So there was a very, because we know that what is Ampere circuital law, right? Ampere circuital law says that whenever we have a surface, right? Whenever we have a surface and the current is passing through the surface, so we make an Amperian loop, right? And we saw that this E dot or this B dot dl, this would be mu naught and the flowing current I influenced. Right? This was the Ampere circuital law, right, Aisha?
Yes.
Yeah, we understood about the Biot-Savart's law, and from the Biot-Savart's law, we derived this Ampere circular law. Right. Whenever we have a surface, and this surface is not a closed surface, this is an open surface. So in open surface, we will have a closed linear, right? So in open surface, we will have a closed linear loop, right? And that we called as Ampere loop. So for this case, this is the Ampere loop, closed Ampere linear, right? And the current is passing through this open surface, and this is the Ampere circular law. So Maxwell did an experiment and found out that, let's say we have a capacitor, right? So let's say we have a capacitor, and we are, so the current is passing through this capacitor, right? Some current, some conduction current. Let's say this is the current which is passing, right? So we are calculating the magnetic field, right? We are calculating the magnetic field using the Ampere circuit law. So let's say we are calculating the magnetic field at this P point. So we want to calculate the magnetic field at this P point. So first, what do? We make an Amperian loop, right? Which is an open surface, and this surface, right? This is not appearing. So let me. Yeah. So this is the Amperian surface that we have, and the current is passing through this surface, right? And we have this Amperian loop. Let's say this radius is R, right? So if I write the Ampere circuit law, so this would be V dot dl, right? And this is mu naught I, right? And then when I, let's say this is these are in the same direction, right? So the angle is 0. So this is V, and dl is mu naught I, and this is V into 2 pi r, right? So we have some certain magnetic. So V is mu naught I by 2 pi r. This is the magnetic field at this point. Is this part understood, Aisha? Is this
Yes,
clear?
I get it.
Yeah. Now what we do is that, let's say this is a positive plate and this is negative plate. So now what we do is that we take another Amperian, right? In the second case, we take another Amperian loop, and now our open surface is not like this. So I have this current which is passing through, right? So let me draw this one, and I have this current, right? And I take the Amperian loop like this. So like a bottle, right? Like a bottle. So this is my surface, right? So this is my surface. Earlier, my surface was what? My surface was, so this is my surface. Okay. So we have this bottle shaped, and this is the cap, which is open, right? So this, there is no surface in this part. So the surface is in this region, right? And if I want to calculate the Amperian loop, so V dot dl. and this is mu naught I enclosed. So in this case, you see that is there any I enclosed in this surface? Is there any I enclosed? Yes, Aisha, is there any I enclosed in this surface?
No.
Right, because there is no current passing through this surface. There is no current passing through this surface. So this is 0. So we will get magnetic field at P point. This is 0, right? But we saw that there is some magnetic field at this P point. So we are using the same Ampere circuital law, but we are getting a different result. So that is contradicting our statement, right? The magnetic field at this point is coming out to be this, but due to this surface, the magnetic field is coming out to be 0, right? Similarly, let's take another surface, because you see there is no current passing through, right? There is no current passing through this region. Now we take another surface, another case, and we again take this capacitor, and we make our Ampere loop like a tiffin box, right? So we have our, this is again open, right? And then we have this bottom of the tiffin box. So this is my surface, right? This is my capacitor, and this is the current which is flowing. And you say, see that the current is not flowing through this surface. So there is no current enclosed by this surface, right? So again, if I use the Ampere circuital law, mu naught, and again I is 0, right? So again I get the magnetic field at this P point, that is 0. So we are taking three different kinds of surfaces, right? Firstly, we took this surface, right? And there was this current passing through this surface. Now, we don't have any surface, so this cap is open, right? We have this bottle shaped thing, and this cap is open. So there is no current passing through this surface, right? And we know that inside the capacitor, there is no conduction current. This current is not passing through inside the capacitor, right? So the magnetic field we found out at this point is 0. Similarly, in this case also. So in this surface, there is no current passing through this surface, right? And we found out that magnetic field at P point is again. So we are using the Ampere circuital law, but we are getting a different magnetic field at the same point. So is this possible? Can we get a different magnetic field at the same point? Yes, guys. Yes, Mariam, did you understand what I'm saying? I'm
Yes,
just,
sir.
yeah, I'm just talking about Ampere circuital law. So in Ampere circuital law, what is the Ampere circuital law? If you have a current passing through this surface, right, then my B dot dl in the closed loop, this loop, right, in this loop, my B dot dl is mu naught and I enclosed. So whatever is this I is flowing, this is moving in this way, and then it is coming up. So this is the Ampere circuital law, right? And this is the Amperian law. So what we did in our experiment, or not our experiment, but Maxwell's experiment, that we have a capacitor, right? and the current is flowing in this way. So there is no current inside, right? And these currents are flowing. And when you want to calculate the magnetic field at this point, right? So we use this surface, and we got this magnetic field. And then we use another surface, this one, right? This lid is open, and this is the surface in which we are calculating the current, right? Or calculating the magnetic field. So there is no current passing through this surface, right? So then this I enclosed is zero, and I am getting a magnetic field which is zero. Similarly, I take this Tiffin box kind of a surface, right? And then I calculate the magnetic field at this P point. So then it is becoming zero, right? So which is contradicting the Ampere circuit law, right? So there may be something which is there, but we can't identify. So Maxwell identify that, let's say, if we have some current which is also passing through this region, right? This current is zero at this point. This is called the conduction current. Conduction current due to flow of the charges, right? So due to flow of charges, we have this conduction current, right? And what is happening inside this capacitor, which is generating some current, right? Because if you want to correct correct the Ampere circuit law, so there must be some current which is passing in this region, right? That will complete this Ampere circuit law. So that is called the Maxwell correction. And he stated that there is some current, passing inside this capacitor, and that is not due to flow of charges. So how these current are generated? These are called the displacement current, right? And these are generated due to change in electric field, as we pointed out, right? That is this possible that change in electric field produces magnetic field, right? So this is the reason of this displacement current. We only, up until now, we understood that flowing charges, only electric current can produce magnetic field. This we understood. But now we are seeing that change in electric field also can produce some magnetic. And that current is called the displacement current, right? Displacement current arises due to change in electric field, right? We already saw that due to change in magnetic field, we had this current, right? Which was I will write this later, but there was some EMF generated, right? There was some EMF generated due to this change in magnetic field, right? So this we understood in Faraday's law.
Sir,
Yes, Maria.
sir, your voice is cracked.
My voice is cracking.
Yes, sir.
Oh, is this cracking for you also, Aisha? Yes, Aisha. Is my voice cracking for you also?
No, sir.
Okay, so Maria, there may be some problem in your side, maybe some internet issues. Yeah, so let us understand what is the displacement current. So we have this parallel plate capacitor, right? So there is some electric field, right? And this is the negative field. So the electric field is in this direction, right? Now you guys tell me that what is the electric field inside the parallel plate capacitor? What is the electric field? Yes, guys. What is the electric field inside the parallel plate capacitor? We did so many times this calculation. Okay, this we understood so many times. What is the electric field inside the capacitor? Who got disconnected? Mariam got disconnected. Okay, so Aisha, what is the electric field due to the sheet? Due to sheet, what is the electric field? Due to positive sheet, this is the electric field, right? Going outward, and that is sigma by 2 epsilon naught. And due to negative, yes, yes, absolutely correct. And due to negative sheet, right, the electric field is incoming, but the magnitude is same. That is also sigma by 2 epsilon naught. And when we connect these plates together, then we have the electric field inside the parallel plate, that is sigma by epsilon naught. Right? Do you remember now, Aisha?
Yes, sir.
So we have this electric, right? Now, now what is, so we have this electric field, and we know that this electric field is, so this is sigma, right? Sigma is how much? Q by A, right?
Yes, sir.
So this is our electric. Now what is electric flux? What is electric flux?
EA positive.
PA cos theta. Now, and let's say area is, so plate is this, so area is with the 0 degree angle. So this is EA, right? So when we calculate this, so this would be E, right, which is Q by A E epsilon naught, and then we have this A. So A cancels, and this would be phi E, right? So this would be phi E, and this is Q by epsilon. And if I want to calculate the change in electric flux, that is the idea, right? Change in electric field. So if I want to calculate the change in electric flux, so this would be d by dt, right? Let me write it in proper manner. So differentiating differentiating both sides with uh, with respect to time, right? So d by dt of electric flux and d by dt of q by epsilon. So this is d phi e by dt, and epsilon naught is constant, and dq by dt. dq by dt is what? That is current, right? So this would be d phi e by dt, and that is I, and let's say that as id, right? By epsilon naught. So ID would be epsilon naught d phi e by dt. So we saw that this change in electric flux also produces this current, right? We were seeing that change in magnetic field, this was producing some current, EMF. Now we are also seeing that change in electric field also some produces some current, right? and this current will have some magnitude. Is this part clear, Aisha?
Yes.
Yes. So this is called the displacement current. Displacement current. So then what is this displacement current? Definition is what? So the current produced by changing the electric flux, right, with respect to time. So this is the displacement. Okay, so now we will see that how can we correct. So Maxwell then corrected this. So then Maxwell corrected this Ampere circular law using the idea of this displacement current. So in between this capacitor, there would be a displacement current, right? And outside the capacitor, there is no displacement current. So this is zero, right? And inside the capacitor, we have this displacement current. So you guys, please note down this part. And then, yeah. So please, this part you note down from the Ampere circuital law. So is this clear, guys? Is this part clear up to this point?
Yes, ma'am.
Please note it down and please let me know whenever you want me to scroll down this. So earlier we saw that whenever we change the magnetic flux, so that produced some EMF. Now we have this changing electric flux and that is also producing some EMF. Yeah, whenever you guys want me to scroll down the screen, please tell me. So in case first, we have a surface from which IC is passing, right? This is the first surface. IC meaning conduction current. Note it. Oh, please note down this part. So in the case second, IC is not passing to this surface. So let's assume a bottle, right? This is a bottle and these are the surfaces, right? In these services, there is no current passing through this service. Right? You see, this is the open. So open lid of the portal. Yes, whenever you guys want me to scroll down the screen, please.
Done, sir.
So please. So again, IC is not passing through the service. Yes, whenever you guys have noted it down, so should I scroll down the screen, guys? This part, right? Done, everyone?
Done, sir.
Then, please note down. This is yes, Maria. What are you saying? You noted. Do you want me to scroll up? Yeah. What are you saying? I cannot hear you properly. Yes. What did you say? My voice is cracking. Okay, so maybe there is some internet, but because my internet is working fine. But yeah, yes. So my internet is working. Am I audible clear now? Am I audible?
Yes, sir.
Good. Yes. Okay, please note down this part. Yes, whenever you guys have noted it down, please.
Done.
Then, okay, so then write about this displacement. Done, everyone.
Done.
Done. So we can understand these scenario in these manner also. That we had this. So they explain this scenario in this way also. That let's say this current is fluid, conduction current, right? And they measure the magnetic field. Now my internet is not stable. Am I audible, everyone?
Yes, sir.
Yes. Good. So now what they do is that they measure the magnetic field at this point due to the magnetic compass, right? So we have the magnetic field at this point, and they also, right? So let's say they take two surfaces, one in this one and the other one in this way. So we have a magnetic field at this point, right? Some magnetic field. And in here, when we calculate the magnetic field, so there is no current passing. So in here, the magnetic field would be zero, right? But when they take a magnetic compass in here, so this shows the deflection, right? And when they take the magnetic compass in here, so this also shows the magnetic deflection. But the Ampere circuital law is saying that there would be no current in this, there would be no magnetic field in this region, right? Because your magnetic field is zero. So the Maxwell said that there would be some there would be some current which is flowing in this region, and that is not due to this movement of charges, but due to change of flux, right? So we have a current which is conduction current in this side, but we have a current which is displacement current in this region. So that is how this circuit is completed. And when we calculate the magnetic field in these regions, then we will get the magnetic field, right? So that is how Maxwell corrected the Ampere circuit law. He said that the total magnetic field in a closed loop, this would be mu naught I total. And I total is how much? So this is the Maxwell's correction. Maxwell's correction in Ampere circuital law, right? So he said that this I would be I total, and this is mu naught IC plus ID, right? And how much is this ID? We have calculated that, right? So ID is epsilon naught d phi E by d. So we have a conduction current due to flow of charges, and then we have displacement current due to this change in electric flux. So that completes this Maxwell's or this Ampere circuit law. So this is the correction. Understood? So this part is the correction part. Is this point clear?
Yes.
Yeah. So please, you guys note it down. So note down from here, right? This is another way of understanding this displacement current. So whenever you guys have noted up to this point, please tell. We don't have not equal to 0, not equal to 0. And this is the correction. Yes, whenever you guys have noted it down, please tell. So where IC is conduction current and IG is displacement current. Yes, noted everyone. Yes, guys, noted.
Done, sir.
Then, Mayam, what about you?
Done.
Okay, so then we have a capacitor, right? And so we have this one. So we have, and then here ID is 0, and we have this ID, and in here IC is 0, and again ID is 0. So in this circuit, the displacement current outside the capacitor is 0, and there is a conduction current outside. Similarly, there is no conduction current inside, but there is non-zero displacement current inside the capacitor. Okay, so then with these corrections, we have set of Maxwell's equation, right? So these Maxwell equations, there are four Maxwell equations. So they tell us that how electric and magnetic field are. So first one is you already know. First one is Gauss law, right? Gauss law for electric field. Okay. So what is the Gauss law? Do you guys remember? What is the Gauss law?
Number of electric,
Yes.
number of electric
Yeah,
field passes through
your voice is very faint. Voice
the
is.
number of electric field line passing through a surface normally.
Yes, absolutely right. Good. So number of electric field lines, right, passing through a surface, that is Q enclosed by epsilon. This is what you're saying, right? So that
Yes,
is
sir.
the Gauss law. Good. And this is for electric. Okay, then we have the Faraday's law, right? What is the Faraday's law? So Faraday's law says that E dot dl is minus of d phi b by dt, right? This is the E dot dl is what? Potential, right? So E dot dl is this one. So this is the Faraday's. Whenever you change the magnetic flux, there would be some EMF generated. So this is Faraday's. And then we have the Gauss law for magnetic field. So what is the Gauss law for magnetic field? Yes, guys, what is the Gauss law for magnetic field?
0.
Yeah, so Gauss law is related with this area, right? So V dot ds. This is the Gauss law for magnetic. So what would be this? What is this, everyone? What are the number of magnetic field lines passing through the area?
Magnetic flux.
Yes, this is zero, right? Because the total magnetic field lines inside a closed loop, so number of outgoing and incoming are same. So you have, if they are outgoing, then that is plus, and if they are incoming, that is minus. So you have plus minus total equal, so that would be zero, right? So this is Gauss law for magnetic. Okay, and last one we just described. So the last one, which is P dot here. This is mu naught and IC plus epsilon naught d phi P by d. So this is the Ampere circuital law, right? So this is the corrected Ampere circuital law. Okay, so these are four equations governs the electromagnetic behavior of any material, right? So these four equations are called the Maxwell's equation. Okay, so this is the whole crux of whatever you have learned from the first chapter up to this chapter. So these, all those things are constrained in these four equations, right? So that is the beauty of these equations, that all the electrodynamics, all the things are concised in these four equations. So these are the Maxwell's four equations. Any doubt, guys? Any question?
No.
Okay, so please note down this part, right? This part and then this Maxwell's four equation. This was Maxwell's correction, right? In the case of the past. Yeah, whenever you guys want me to scroll down the screen, guys, please. Yeah. Then, Maria, what about you? Noted. This chapter is pretty small. Yes, Maria, noted it down. Yes, Maria, noted. Okay, so yeah, and the next thing is next thing is electromagnetic waves. So what are electromagnetic waves and how they are generated, right? So the idea is that, but this is out of the scope of our syllabus. But the idea is that whenever we combine these four equations, then we get a wave equation that tells us that the electric field and the magnetic field, they are these charges are moving like a electromagnetic wave, right? So whenever we combine these four equations, then we will get a wave equation. And that will tell us that the charges are moving like a electromagnetic wave. But derivation is not there for the syllabus. But from the argument, we will understand that how the moving charges can produce electromagnetic waves, right? So to generate the electromagnetic waves, the first criteria is that the charges are oscillate. The charges are accelerating, right? So whenever we have an accelerating charges, right? Whenever we have an accelerating charges, then they will produce the electromagnetic waves, right? So let's take an example of an oscillating charges, right? Note is here that the rest charge or the charges moving with constant speed will not produce electromagnetic wave, right? So whenever we have charges which are rest and but which are moving with a constant speed, so they will not produce electromagnetic wave, right? Rest charge will generate what? Rest charge will generate what? First chapter, right? First chapter. Whenever we have a rest charge, that will generate or that will produce what? Electrostatic field, right? And whenever we have moving charges, so that will produce the magnetic field. But those will not produce the electromagnetic wave. Electromagnetic wave means that the electric field or magnetic field that is changing with respect to time, right? But the rest charges produces electric field, right? And that is not changing with time, right? There is no time dependence. And whenever we have constant moving charge, right? Moving charge with a constant with a constant velocity or speed. So this will produce the magnetic field, but that is also not dependent upon time. So that is not changing with time, right? So then whenever we have and accelerating charges. So the charges are accelerating, they will produce electromagnetic waves, right? And we can take an example of, so we can take an example of oscillating charges, right? Because we cannot, in our scope of the syllabus, we cannot arrive, we cannot derive. So we will understand this argument. So let's say we have oscillating charges, right? So these oscillating charges will produce some acceleration. So these are oscillating, so they will contain some acceleration, right? And due to this oscillation, they will have some magnetic field, right? The charges are oscillating, so they will produce some magnetic field. But those magnetic fields are changing with time because the charges are oscillating. And whenever we have a changing magnetic field with time, changing magnetic field, so that will create some electric field. And that electric field is also changing with time. So whenever we have an electric field which is changing with time, so that will create the magnetic field. And that magnetic field is also changing with time. So this process will continue to go on, right? So these oscillating charges will produce electromagnetic wave. Is this argument clear, Aisha? That whenever we have an oscillating charges, so this will have some acceleration. And these oscillating charges will produce magnetic field. But that will not be a constant magnetic field, right? With respect to time, it will change because these oscillating charges will produce a change in magnetic field, changing magnetic field with respect to time. And the magnetic field which are changing with respect to time, that will produce the electric field. And that will also be changing with time. So simultaneously, that will also produce the magnetic. And this process will go on, right? So this is how these electromagnetic waves are generated. Is this point clear, Aisha?
Yes.
Okay, so then the idea is that how they propagate in this space, right? So how they propagate in this space. So we have a three-dimensional thing, right? So we have a three-dimensional object, and let's say space. So we have a three-dimensional space, and this is z-axis, right? This is let's say y-axis, or let me write it as this is x-axis, right? And let's say this is y-axis. So waves are propagating in z-axis, but let's say electric field. So electric field is propagating in x and z plane, right? So this is propagating like this one. Okay. So this electric field is going in this way, and then we have this. So this is our electric, and this is in the x and z plane. Similarly, we have a magnetic field, right? So this is our E. And then we have this magnetic field which is in the, right? So this is in the YZ plane. right? So this is in the YZ. And this is our magnet. So this is how these electric and magnetic electromagnetic propagates, right? The electromagnetic wave propagate in Z direction. This propagate in XZ plane and this propagate in YZ plane, right? So the electric field is propagating in this manner, E naught, and this is in X. So this is sine of kz minus omega t, right? And then we have this magnetic field. This is V naught and sine of kz minus omega t, right? So this is how the electromagnetic wave propagates. And you can see that these electric field and magnetic field, they are always perpendicular to each other. So you see that this is in the X direction and this is in the Y direction. So they are always perpendicular to each other, right? And they propagate in the Z direction, where this K is called the wave vector. This is called the wave vector, and this is 2 pi by lambda. And you guys already know that this omega is angular frequency, which is 2 pi by t. This is the angular frequency, right? So this is how this wave propagates. You guys please note it down, and then you will understand about it. So you see that rest and constant charges cannot produce the electromagnetic wave. So only the accelerating charges produce these electromagnetic field, right? Continuously, your electric and magnetic field are generated, and they are varying with time. Any doubt in this electromagnetic waves, guys? Any doubt?
No, sir.
Yeah, so please note it down. Yeah, whenever you guys want me to scroll down the guys, please.
Okay, sir.
Done. Yes, noted, everyone. Yes.
Done, sir.
Okay. So, so this is this is how this electric and magnetic field propagates in space, right? So this part tells us that in space how this electric field is behaving, and this part tells us that in time how this electric field is changed. Similarly, this is the space part, and this is the time part. And remember, this is a vector quantity, right? So this is the magnitude of this wave vector, right? And the speed of propagation. So speed of propagation is given by speed of propagation is given by omega by k, right? And let's say in a vacuum. So in a vacuum, the speed of propagation would be speed of light. So this is c and this is omega by k. So angular frequency would be ck. Okay. And you guys also know that how this, so you know that we have this electric field, right, which is E naught and sine kz minus omega t, right? And we have this magnetic field, which is B naught and sine of kz minus omega t. So this E naught and B naught are the maximum values, right? And whenever we divide E naught by B naught, so then we get the speed of light. So this is one relation, right? Okay, so these are important relations. You guys please. So this electromagnetic waves are complete, and the next topic is electromagnetic spectra. So that will also take one class, and then this chapter is over. This chapter was a very small chapter, only two topics. One is displacement current, Maxwell's correction, and then second topic is electromagnetic waves and how the electromagnetic waves are propagating in space and time. So that was the idea of this chapter, right? So in the next class, we will talk about the electromagnetic spectrum. Whenever you guys have noted it down, please tell me.
Done, sir.
Done. Okay, so there would be a class assessment test today, right? So can you guys log into your Learnivio account and please check whether you have this test activated or not. So please look into that and tell me whether you have this test activated.
No, it's not active.
It's not active.
No, sir.
Okay, so we'll end the class as for now, and in the next class we'll take that assessment. Okay, next class. So Allah Hafiz, guys, and Allah Hafiz, and see you in the next class.
Thank you, sir.
Yes. Bye, bye.